a lot of people are talking about a second wave of COVID-19. And I don't think that is really accurate if what has happened is you've suppressed the initial wave, but not completely, you relax on the suppression and it grows again. A true second wave would be if you've eliminated all community spread and it comes in again from outside. A little like what happened in New Zealand. So let's have a look at a very simplified simulation to try to understand what's really going on. So first of all, this is a picture that looks at what would happen if it just spread out of control. It's based on a model where people are either susceptible, they haven't been exposed to the virus yet and can catch it, they're exposed, which means that they have caught it, but they aren't contagious yet, infectious, or they've recovered. And we're not going to model deaths here or differences in how severely people get it. So to get to this picture, the model assumes that when everyone is susceptible, each person who's infected infects another person every 4 days. It takes 3 days to go from exposed to infectious, and 10 days to go from infectious to recovered. So 10 days divided by the 4 days it takes on average to infect another person gives you an average of 2.5 people infected per initial infection. That's assuming everyone else is still susceptible. And that is a number that we call R0. And R0, given these numbers, would be 2.5. The real infection, it varies a fair amount because it does depend on things like how people mix in society. So if this thing has run to completion, you'll notice that there's another number under the R0 called plain R, often called RT, which means the value of R at a particular time, and that's down to 0.26. And RT is less than 1, the number of infections starts to drop off. So let's look at a bit more detail of this picture. Notice this vertical line where the two pink lines peak, and that crosses this horizontal line, which is at 60% of the entire population having been infected, including those who've recovered. The grey curve is those who've recovered, the light pink is exposed, and the dark pink is infectious, and the light and dark pink eventually merge because everyone who's exposed gets infectious. So that's 60% of the population. The thing to understand from this picture is that 60% is the turning point of the increase in infections. It's not the end point. At the end point, which is the point where the grey line levels off, is almost 90% of the population eventually is infected. So don't take the 60% number as an indication of the maximum who are likely to ever get infected. If you let the thing run out of control, it's a much higher fraction. So let's have a look at what happens at the opening of a pandemic like this. Now, the number of infections starts going up really fast. And so visualize early days of New York or London or Italy or Spain, so on. Hospitals are getting overwhelmed. And R0 started at 2.5. RT is now down to about 2 because it's no longer true that everyone who an infected person meets is still susceptible, but it would still increase very fast if we did nothing at this point. So we now take a close look at this number. It infects 1 every 4 days. And remember that is under the initial conditions where everyone is susceptible, so it is a bit lower now. But even so, it's still too high. So what can we do? Well, at this point, over 20% of the population has been infected. What would happen if we start introducing non-pharmaceutical interventions, masking, distancing, hygiene, ventilation, and so on? And let's say we are unrealistically quick about doing that. We turn on a dime and suddenly we're doing all of those things, and we now only infect 1 new person per 10 days. So that would be like having R0 equal to 1, but because around 20% of the population is already infected, it means effective RT drops below 1, because R0 is 1 would apply if everyone is still susceptible. And we see now our pink curves start dropping off fairly steeply, And we keep going with that for a while, up to the point where nearly 40% of the population has been infected, which is a lot less than where it is heading for if we did nothing. But notice we're still well below that horizontal line for herd immunity, which has dropped off the picture now because we're faking the effect of a less contagious disease. And if the R0 value is 1, then the herd immunity level will be right at the bottom, because technically herd immunity happens when whatever R0 was initially, the current value of R has hit 1, and if more people get infected, it starts to drop off. So we have changed our effective infectiousness of the disease to infecting one susceptible person every 10 days. And if a person stays infectious for 10 days, then that's why we get the R0 as 1 thing. But as I said before, R0 is when everyone is still susceptible. So we've faked the effect of a less infectious disease. And we've done this by reducing human contact, because we don't have any pharmaceuticals to slow the course of the disease by making people less infectious or infectious for a shorter time and so on. So it's non-pharmaceutical interventions that have done this. So that looks under control. And note where the herd immunity level is, we haven't reached that. That should be a bit of an alarm signal, because if we let it go again, we haven't reached the point where it would naturally subside. So what would happen then if we now relax the measures, noting that we haven't, our peak was not at the herd immunity level, and we now go back to a mode where it infects one person every 4 days, noting at this point around 40% were infected. And so we've relaxed our measures and see what happens next. Remember, the susceptible group of the population, around 57%, so a bit over 40% infected. It's now allowed to run to completion with no further measures to slow it down. And this is what the picture looks like. We end up with around 75% of the population eventually getting sick and recovering. Again, noting I don't model deaths at all here. And it's better than 90%, but it's still a pretty high fraction of the population. Notice also the second peak looks a lot lower than the first peak, which is not actually what we're seeing in countries like Britain, where the second peak is a lot higher than the first. But we'll get shortly to what the inaccuracies are. But if this graph represents the true number of infections, we would expect something that looks a bit like this. Right, so how real is this? Well, first of all, real populations aren't uniform. A big, diverse country like India, United States, South Africa has very different regional variations. And even a small country has differences in things like how high density living and transport and so on are. The other thing is that the first wave was underestimated, probably far more than this supposed second wave, because many countries didn't have adequate testing in place. So in Britain, for example, and Italy, New York, those other places that had it very badly, the testing didn't go very much beyond the very, very serious cases, which is why it didn't look as if the numbers were as big as they do now in many of those countries, and yet the hospitalizations and deaths were much worse then. The other thing is this model doesn't take into account deaths, and it assumes all who recover are immune, which isn't necessarily true. So a few things to take home then. R0 depends on both the disease and our behavior. So the whole point of non-pharmaceutical interventions is to fake the effect of a less infectious disease by modeling one where people behave differently and therefore spread it more slowly. So if we stop the NPIs, it takes off again. Maybe not quite as steeply as it did before, because we're starting from a higher base of people who are no longer susceptible, but you can get it again. And although the number of cases reported so far is quite low, and most of them seem to have had a fairly mild form of it the second time. There has been at least one case reported where somebody got it again and got badly. So we can't rely on simply slowing down the NPIs, then allowing to take off again and hoping we've learned enough about treatment and that people who had it before won't get it again. This is why a vaccine is really the best bet to stopping it. We know the herd immunity level is around 60%. It may be higher in societies where there's more social mixing, but we can work that out. We can make sure that at least that level is vaccinated and immune all at once. Whereas if we rely on the natural progress of the disease, it could be that by the time we've hit the herd immunity level, the first round of people who were infected become susceptible again. We don't know that. We don't have the data for it. So at this point, the vaccine is our best option.